Welcome to the solutions to the Regents Physics Momentum problem set, problems number 15 through 17. Problem 15. A car moving at 10 meters per second crashes into a barrier and stops in 0.050 seconds. There's a 20 kilogram child in the car. Assume the child's velocity is changed by the same amount as the car's in the same time period. What is the average force on the child? What is the mass of the child whose weight equals the average force calculated in part A? If 1 kilogram weighs 2.2 pounds, could you lift the mass calculated in part B with your arm? According to these answers, why would it be advisable to use a proper infant restraint rather than to hold a child on your lap? Great practical application question here. We start off with A, which is looking for the force, gave us the time, initial velocity, final velocity is 0, and gave us the mass of the child. Sounds like impulse momentum theorem. The change in momentum is due to a change in velocity, so we have F times T equals M delta V. Force times the time, 0.050 seconds, equals the mass, 20 kilograms, times the change in velocity, final minus initial. Final is 0 minus initial of 10. Do the algebra, solve for F, and we have a negative 4,000 Newton force. To two digits, 4.0 times 10 to the third newtons. Negative because the force acts opposite to the motion of the child itself. B, what is the mass of the object whose weight equals the force calculated in part A? All they're asking us to do here is take this force, pretend its weight, and what would the mass be? So we're going to do a quick little W equals mg. We substitute our force for the weight equals m times 9.81 meters per second squared. Solve for the mass, and we get 408 kilograms. Part C asks, okay, if 1 kilogram weighs 2.2 pounds, could you lift the mass calculated in part B with your arm? So they want us to convert this mass to pounds. It's a quick little dimensional analysis calculation. You'd multiply in your factor here. Kilograms would go in the denominator. Pounds would go in the numerator. So kilograms cancel. We're told 2.2 pounds in 1 kilogram. And so 408 times 2.2 is 898 pounds. And of course, the answer to that, could you lift that mass with your arm? And that answer, of course, would be no. 898 pounds. So, according to the answers, why would it be advisable to use a proper infant restraint rather than hold a child on your lap? If you caught on to what this question is doing, it's taking the force that was exerted on a child and converted it to a weight that you could comprehend. So, in other words, a force of 4,000 newtons is the same thing as 898 pounds. This gives you an idea of the force required to restrain the child. You've already established that you couldn't hold or lift that mass, that amount of weight with your arm, that amount of force with your arm. And so it would be advisable to put the infant in a restraint system which could properly restrain the individual instead of you trying to do it, because you're not going to be able to do it. So these people who hold a child on their lap while they're driving are absolute idiots doing that. Note this is only a 10 meter per second crash. Remembering that 60 miles per hour is 27 meters per second, we are looking at a speed that is about 25 miles per hour here, approximation. All right, let's move on to question 16. We have marble A of mass 5 grams moves at 20 centimeters per second, collides with the second marble B of mass 10 grams, moving at 10 centimeters per second in the same direction. After the collision, marble A continues at the speed of 8 centimeters per second in the same direction. Draw before and after diagram, and what is the velocity of marble B after the collision? We start with the before and after diagram, which is critically important to the success in this question. Here we have A of 5 grams traveling at 20 centimeters per second, B at 10 grams traveling at 10 centimeters per second. Looking at the diagram, it's clear what's happening here is that A catches up to B, hits B, and then after, A continues in the same line at 8 centimeters per second, and we're asked to find the velocity at which B continues on, and both are still separate after the collision. In order to solve this is a conservation of momentum problem. P before equals P after. So we have 5 times 20. Sorry about that, I got interrupted there. So I'm going to start over with a substitution. We have 5 grams at 20 centimeters per second plus 10 grams at 10 centimeters per second. Both objects have momentum before the collision, and they're not together, so we have them separate momenta for each one, and they're added because they're both moving in the same direction. After collision, both objects have momentum, and they're also separate. So we have our 5 grams times our 8 centimeters per second plus our 10 grams times VF. Now, notice that I did not change grams to kilograms, and I did not change centimeters per second to meters per second. Could you do the problem this way? Yes. But note, to change to grams, what you would do is you divide every single one of these by 1,000. In doing that mathematically, it's a wash in the end anyway. Converting each of the velocities, you divide each one of these by 100. Same thing. So, what's important to note here is that when you conserve momentum, you do not need to convert units as long as all your masses are in the same unit and all your velocities are in the same unit. And when you're done, that you express your answer with the correct units. Doing the algebra here, you'd multiply 5 times 20, which is 100, 10 times 10, which is 100, add them together, that's 200. 5 times 8 is 40, subtract. So that sounds to me like 200 minus 40 would be 160. 160 divided by 10 to solve for VF would be 16 centimeters per second. All right, lastly we have number 17. 2 students on roller skates stand face to face, then push each other away. One student has a mass of 90 kilograms and the other student has a mass of 60 kilograms. Draw a before and after diagram. Find the ratio of the students' velocities just after their hands lose contact. Which student has greater speed and which student pushed harder? All right, let's start with the before and after. Beforehand, we have the 60 kilogram and the 90 kilogram both at rest. They push against each other, and afterward, the 60 kilogram will move off in this direction, and the 90 kilogram will move off in this direction. Okay? Next, we're asked to find the ratio of the students' velocities after their hands lose contact. Going to conserve momentum to do that. P before equals P after. What objects, if any, have momentum beforehand? The answer is none of them, because none of them are moving. So the momentum before is 0. What objects, if any, have momentum after? They both do, and they're in opposite directions. So we have 60 times VW minus 90 times VL. And the reason for that is that if we call VW positive, then VL has to be negative. You can do it the other way around if you want. You could go 90 times VL minus 60 times VW, doesn't matter. We add 90 VL to both sides, and they want a ratio of the students' velocities. So that means we simply need to get the speeds as a ratio and get rid of the numbers onto the other side, and that would give us our ratio. So we've divided both sides by VW and divided both sides by 90. This would give us VL over VW equals 60 over 90, which is 2 to 3. So the ratio of the speed is VL to VW is 2 to 3. If you solved it for VW to VL, the ratio would be 3 to 2. Okay? So which student has the greater speed? Well, clearly the one that has the greater speed is going to be the one with less mass. You can reason that out a number of ways. What you can see here is that the momentum of these two people is equal to each other. So that means the one with the less mass has to have greater velocity to compensate for this guy who has greater mass and who would have lower velocity. And part D, which student pushed harder? This is a trick question because you might remember Newton's third law. For every action, there's an equal and opposite reaction. Therefore, the force that this guy exerts on the little guy is the same as the force the little guy exerts on the big guy. That'll do it on our set of problems for today, 15 through 17. More to come as we complete number 18 in class tomorrow.